And that result basically looks like this. And I'm pretty sure you haven't seen that kind of a plot before. As I mentioned, one of the things to look for in the scale factor plot is its inflection point. According to lambda CDM, roughly speaking, that should occur at 0.5 look-back time, about 6 to 7 billion years ago. Well, that was what we attempted to do with the data set. We have to take a derivative of that data set, and this was model independent, so you can work straight with the raw supernova data. And in doing so, instead of finding a minimum, we found several minima. Each of those minima results in some measurement that, for example, explains why there's been a huge spread in transition Z's in the literature. So that's one of the answers that this approach gives right away. The frequency that you see there is approximately 7 cycles over the lifespan of the universe, 13.8 billion years. Now we've coined a new term for that, Hubble Hertz HHZ here. So that 1 Hubble Hertz, frequency is very convenient to use here. 1 Hubble Hertz is 1 cycle over 1 Hubble time. So the frequency we found is 7 Hubble Hertz. And of course, smoothing is not the best way to do this. That was our first attempt. You need more sophisticated methods to analyze this data. So one of the other approaches we used was Fourier analysis. And again, no matter what approach we tried, smoothing, binning, different variations, looking at a time derivative of the scale factor, we always found that same 7 Hubble Hertz signal. But in the case of the Fourier analysis, we found 2 more frequencies, the second and the third harmonics of that. Now, I was not able to reproduce the harmonic effect in any way as an artifact, so we're assuming that's real. So the 3 frequencies actually occurred together, and we always saw them. Another important test is autocorrelation. That's a very powerful test. The autocorrelation signal is extremely good and is representative of a higher signal-to-noise that we got later in the analysis. We were able to improve the signal-to-noise to approximately a factor of 3, so that's a 3-to-1 signal-to-noise in this data that we've been presenting. And we actually used the autocorrelation function to peak that. One of the other things we did was develop a model, a full simulation of the exact noise distribution through the model, carrying both lambda CDM through it and a model that I'll shortly describe. And we were able to estimate the likelihood that such a signal, the 7 Hubble Hertz signal, can occur as a false call. That number is 1 in 10 times. In other words, I put pure noise into this model, the simulation, and through the filters that I use, and you can actually, as anyone knows working with filters, can come out with a real signal. This happens about 1 in 10 times. But it happens for each of the frequencies. So there are 3 of them. So all in all, if the harmonics are real, then the likelihood of seeing all 3 simultaneously is somewhere between 1 in 100 and 1 in 1,000. Now we're approaching 2 to 3 sigma of significance. We also developed a model to describe the oscillations, a scalar field dark matter model, and this is based on Linde's chaotic inflation, but into the present epoch. And it uses a simple harmonic oscillator potential. This model is so tightly constrained, only the frequency is adjustable, yet the frequency match to the actual observations was extremely good. The important point to remember about this model is the fact that we use the energy density of the scalar field, omega phi, to replace the dark matter energy density in lambda CDM, literally. So that means, the bottom line, the oscillating scalar field that we're talking about is the dark matter. And if you believe this is a quantum theory, that means this frequency corresponds to a particle mass of only 10 to the minus 32 electron volts. Definitely not a WIMP. This is the comparison of the scalar model that we just talked about together with lambda CDM. And if you look at that plot, you'll see that both of them are indistinguishable up to about a look-back time 0.1, between 0.05 and 0.1. Then they separate. So this resolved a number of issues. Number one, it immediately explains the issues between the discrepancy of the W mass omegas and the Planck omegas. The early dip means that the universe suddenly had a reduction, a serious reduction in its expansion rate, and that implies earlier galaxy formation that's been observed but is not well understood, so it explains that. And one of the outputs of this, a thought to keep in mind, is a prediction would be looking for the periodicity that I just described in the large-scale structure of the universe. Thank you.